Simpson's paradox. So first, what is the paradox? So everyone know what is paradox, right? And we're talking about the math. We're talking about the quantitative, which means that we need to find a way to understand the results from data analysis. Okay, so you will see here, and this paradox just give us, if we did it wrong, if we did the analysis wrong, we will find a wrong answer or a wrong explanation or wrong conclusion. Okay. And here, Simpson's paradox is improbability or statistic to data analysis. And let me highlight, we have to make sure one, in which a trend or a pattern appears in different groups of data, like individual data or local data, but disappears or reverse when these groups are combined. Okay, that makes sense? If we have a whole data here, if I cut the data into two parts, I look at one part, I get a pattern. I look at the other part, I get the same pattern. Okay. However, I put the two data together, I look at the whole data. All we say is the overall. If I look at the overall and then the pattern disappear or completely reverse, do you think that's possible? Yeah, it is. I will show you 3 examples today. Okay, you will see. It's very strange. Okay, when you look at the results, you should feel very strange. Okay, but that's possible. Now we came from the Berkeley gender bias cases. Okay, case in the history. This is a real case. Simpson is the person, okay, who published the report, so that we use the name we call Simpson's paradox. It's not a long ago. You can see it's 1973-4. So in Berkeley University, okay. So California, University of California in Berkeley. Okay, you can see. But look at the admission to graduate school. So in this university, okay. And we have a data. So this is the global data or overall. I want to look at the first data. And for this topic, the first topic we need to understand is how to read the data, okay? And how do you figure out the table by yourself. So can you look at the first? This is a contingent table, or simply say it's just a data a summary of the data. We have total applicants to the school, graduate school in University of California, Berkeley, and then including 8,442. This number is the male student, okay, the applicants, and then 4,321 is for female. And then I look at among these 8,000, and we have 44% admitted. What does 44% mean? Means 44% of these 8,000, so that we can time them together. Okay, we know how many male students admitted to the school, right? About half, less than half, probably like 4,000, probably like 4,000. You'll see it's a huge school. And then how many percentage of the female student? Is only 35%. So you can do calculation. And this number, 35% of 4,000, which means time together. So this number times 0.35, you should find how many female students admitted to the school. Okay, so we don't look at the real number of the students successfully admitted to the school, but we only look at the percentage. So can you look at this percent? 44% and 35%. If we only look at these two numbers, what kind of a conclusion we can make? So probably this school is unfair, is discrimination, is unfair to female students. Is that okay? Because 35% is lower, much lower than 44%. Okay, If we can get the same percentage, that's the best. Of course, that's fair. But this time, okay, so we have only 35. So we can make the first conclusion based on this data. Okay, it's not that we make, okay, in the history and the Simpson published the work. Okay, the first discussion is for these two data. Definitely we have some kind of discrimination. Okay, makes sense, right? So I can make a conclusion. This conclusion is based on the overall data. And later you will see what is the individual data. Overall means we just look at the whole, see? And among all the female students, okay, 35% admitted. Among all the male students, 44%. And these two number, this is much bigger. Okay, this is larger, this is small. And so that we can say like this kind of conclusion. The score is unfair. Okay, so we say is unfair to female student or female applicants, okay, or the gender bias, okay, is that okay? Or we know this is just a kind of bias. Can we make this conclusion? Because 35 is much smaller than 44. Okay. However, we'll look at another. Any question so far for this report? If I look at the data, overall data, I can get a conclusion. You also can get this conclusion, right? Okay. Because the percentage for male students is much smaller than the percentage of the male student. Okay. Can we look at the second? I just tell you this table is just some detail of all the data from University of California. Okay, so the same data. We just look at each department of the school. So like A department probably like so language or English, or like F probably like mathematics, or like this is physics. We did not have the information here, but if you look at, you check back to the history, we do have all the details about okay, so the original data. So this is not a fake data, okay, this is a real data. And now means so far we look at the detail of the original data set, or we look at individual. Okay, if the before we call the overall, if before we call the overall, and then this should be individual data. Okay, department, okay, by department. Can you look at them? So the first department, how many percentage? This is the number of the students applied. This is the number of the female student applying. And then we look at the percentage, because the first data, we look at the percentage, overall percentage. And then we look at the individual percentage of the admission. Can you compare 62 and 82% for the first A department? Which number is bigger? 82 is much bigger, right? Okay, so therefore this is small. So can you look at it? This number is small. Okay, for the first, for A, this is small, smaller. And then the same. Look at the B. So we get the same. But look at the B. This is a B department. This is also smaller. 63 is less than 68. This is what does smaller mean? Smaller means not good, right? Okay, so it's unfair. Similar as See, this percentage is smaller for female student. So it's unfair discrimination, kind of. And then how about the C? No, C is not. I just ignore C. So C is not. So we look at the D. Yes, D. It is. So now 33% is less than 35%. This is smaller. Okay, let me just circle. So that D department is unfair for male students. Can you see? We look at this color is for male student. And then look at two more department. This is the major department in the school at that time, okay? So other is a smaller department, okay? So for department E, so 28, no, this is not. So smaller for female student. However, we look at the last, F department, 6% is less than 7%. This is smaller too. Okay, let me just circle. Means what? Among the total 6 department, this one unfair for male students, right? The gender discrimination now completely reversed. And then this is also unfair for men, unfair for men, unfair for men. And the total 6 department, we have 4 department unfair to male student. That is make sense? We based on the same data, just the same data. So it's very strange. So are you feeling it's a little strange? So let me make a conclusion now. The same data. So this time I make this conclusion. Of course, now it's based on individual data. But it's still the same data sets, okay, from the history. So still the same, we talk about it. And this kind of conclusion. Among 6 department, 4 department, this is the major department at that time. 4 department unfair to male students. So that I can say the school is unfair to male student. And can you see? So now is unfair to men. And here at the beginning is unfair to female students. How could that be? These are based on the individual data. But we know it's the same data sets. Just the first, we look at the total. And then the second, I look at the detail. Do you think if that's possible? Yeah, very strange. And so have you feeling? Is this strange? We think about it similar like this. Okay, so most of the department unfair, the percentage is lower for male. We put them together. The overall percentage should be also lower than the female students, right? But it is not. It is not. That's the real data. Have you found something strange? At least you have some kind of a feeling, right? Okay, that's because something wrong, whatever. But that's a phenomena. Everyone, have you gathered what is the Simpson's paradox first? Yeah. And that's the beginning I just showed you. If you look at it, the overall, if you look at it, the individual data, we have a pattern. But if you put the data together, combine the data, the pattern disappear or completely reverse. Have you seen? So this is the gender bias. It's completely reverse. Okay. If you look at the overall unfair to female students, if I look at the detail, unfair to male students. And the history, definitely we publish it. Okay. So we publish this both of the results. Okay. So therefore we have a a big discussion. So which one is true? Should be one is true, another is false, or both of them are false, right? It's impossible both true. Okay. I will look at the reason a little bit later after this example. One more example, everyone. Are you here, everyone? Can you just let me know? If I hear, listen to me, can you type yes? Because someone probably walk away from us. I'm not sure. Okay, good. Thank you. Yeah, good. Thank you. Most of you are here. Do you have a question? Any question? If you have a question, can you raise your hand to let me know? Do you have a question? Can you raise your hand? No, any question? Okay, so let's go to the second example. And this data is empty. Okay, so let me find it empty. And this data this time, okay, is also it is also a real case, okay, and kind of a clinical trial from a hospital. I did not put the resource here, okay, so you can find the resource from the textbook. And this is the real data. How do you read this data first? Can you read this data? And this we call the contingency table. Okay, it's just a table of the data. If I look at this first and look at it, 1, 2, 3, 4 group. What is group 1 mean? What is group 2 mean? What is group 3? What is group 4? And this is from like a clinical trial from a hospital talking about the kidney stone treatment. We have the first column is treatment A. Okay, the second column is the second treatment. We call it treatment B. Whatever, or you can just think about it is drug A or drug B. We have 2 ways to treat the kidney stone. And we need to look at which treatment is better. That's the purpose, okay? So therefore, we need to enroll some patients to see if treatment A is better than treatment B, or treatment B is better than treatment A based on the data. Make sense, right? And then look at them. So we cut the group into 4. We cut all the patient. Later we will find how many total patients do we have, okay? But group 1 is this. The first column treatment A means these are how many? See, this is the number of the patient in group 1. Means in group 1 we have 87 total patient. So how do you say this is the number of patient in group 1. What is group 1 means? Group 1 means with the small stones. Suppose the patient has a small stone in the kidney, and then use drug treatment or whatever treatment A. So that this group makes sense. We have 87 patient with the small kidney stones and treated by treatment A. Okay, that makes sense, right? And then we'll look at this 81 means success. This is the number of success. This is means among, or we say is like this. Say 81 patient success, okay. Get a successful outcome. That makes sense. How many total? 87. And then 6 patient okay, did not receive a good outcome, but 81 patients out of 87 received a good outcome. So probably the small kidney stone disappear after the treatment, after some time. And we usually call it this is success. So we have 81 success out of 87. If you do calculation, so everyone, if you do calculation, okay, it's easy to get it. 81 success out of 87. See, that's a 0.93. 0.93 times 100, which is 93%, right? So therefore, we get this 93% is the success rate. So therefore, I get this number. Definitely, usually we look at this number. This is the success rate. This. Success rate in this clinical trial for this group. Make sense? So this is how we read the data. And then now, so anyone can tell me what this mean? What group 2 mean? What's the 234 mean? What is 270? What is the 87% mean? Can you guess what does this number mean now? Anyone? Chris, can you tell us your think? What's this group mean? What is this number? Can we read it? Fiona already typed. Fiona says 2. Let me just read the data. Okay, so Chris, if you have something to say, you can tell us. Fiona says 234 success out of 270 patients. So that 87% success rate. Yes, very good. Everyone get? I think everyone know how to read it. Okay. So Chris, I will not ask you to do. Is that okay? Or anyone you have a question? And this means 234 success out of 270 total patient in group 2. What is group 2 mean? Means 270 patient with a small stone treated B, okay, in this group. And therefore, to calculation, the success rate is 87%. This is not a good number, okay? This is the success rate. And everyone now, can you look at it? If a patient is that okay? If I look at the first row, if we compare group 1 to group 2, because both group for the patient with the small stones, so therefore we really can compare, right? We can do kind of a comparison for both group with the small stones, and see treatment A with success rate much higher than the treatment B, right? 93 is higher than 87. Is that make sense? Okay, from here, we easily get something. Okay, the first. For this small stone, treatment A, so let me put it somewhere. Can I put it here? So 93% is higher, bigger than 87%. This means treatment A is better than B for small stone, right? So A is better than B, the treatment B for small stone patient. And you can think about it. Is that a conclusion? Okay, for small stone patient. Okay, let me just simply say, I basically the first, and then do the same analysis. Can you do the same analysis for large stones, which is the another row. So let's look at it. Okay, it's over here. Group 3 means largest down patient with the treatment A, and the total patient two CKD3 patient. And out of 2 CKD3, 192 success. The success rate is 73%. 73 is not a good number. However, group 4, the number is even worse. Okay, 55 success out of total 80, and the success rate is 69%. Can you see? We get the same conclusion. Here, 73 is higher than 69. Therefore, if we look at a large stone now, and the first we look at a small stone, we get this conclusion. And then the same do the second. Because 73% is still higher than 69%. So I make this small conclusion. Treatment A is better than treatment B for large stone patient. Oh, what does that mean? No, finally, it means no matter the patient is with large kidney stone or small kidney stone, and the patient should choose treatment A, right? Because based on the data, treatment A is always better than treatment B. Is that true? Do you think? Right? Yeah, look at the logical, right? So far. So therefore, so let me put it somewhere up front. This is the comparison for the individual data. How do you say? Let me put the results here. So these are two. So therefore, I get this conclusion. I put here conclusion. So this time is based on individual data. Okay, whatever. So this kind of conclusion, A, always better than B. No matter large stone or small stone, right? Okay, so that's the data. That's the one conclusion, but based on the individual. Now, I will not do the individual. Are you here, everyone? Does this make sense to you? Okay, and then we look at the overall, we just put the data together. Can we do a calculation by ourselves, everyone? I look at the group 1 and the group 3. And these both means I just combine. Okay, so this box. So now we look at this box is just a combine. Group 1 and group 3. So these box I just combine. I put them together. Combine group 2 and group 4. So group 1 and 3 means the patient use treatment A. Okay, so this means treatment A. And now these two group compound put together means the patient with treatment A, just treatment A. So combine these two, no matter is large stone or small stone, but both group 2 and 4 use treatment B. I will not look at the detail. I just look at it. Okay. How many patients use treatment A? How many patients use treatment B? How many? 83. Please, this is the calculation, so you need to know how to do by yourself. How many total patients treat use A? This is 83. These 2 CKD3, so therefore I add together. Can you see? Now, what this number? This number is 87 plus 263. Is that true? I put these two numbers together. Of course, if you do calculation, 263 should be 350 exactly. Okay. Or you see, 73 patient there, 263 patient here. Add together, 350. Okay, so that's the number how we get it. That's the total patient treated 8. And how many success? Of course, I have a calculation in this way. I count how many success here, 81 success. How many success here? Let me use this. How many success here is 92. So that the total is 273 because 81 plus 192. So you can see 81 plus 192. Of course, how many? I get 273. So therefore, 273 success out of 350, right? So we look at the number over 350. 0.78, which is 78 percentage. Can you see? I know how to do. I just put these two groups together. I get the overall. This we call the overall, okay? And the previous analysis is the individual. So now here, usually we have a name called like overall. Put it together, combine together. See, the overall success is this 78%. I leave the same calculation for you. Okay, to combine group 2 and the group 4, look at the treatment B. And this number plus this number 350 again. 234 plus 55, I get a 289. So that 289 out of 350 to calculation, you get 83%, 83. And then now if I do this, see, I just ignore the top detail. I ignore what's the data for the small stone. I ignore what's the detail for the large stone. I put them together where I have the overall data. This data, nothing wrong, right? So everyone look at it. Anything wrong? And we did the calculation, that's true. What kind of a conclusion you can make now? Which treatment is better now? So anyone? The treatment B is better. Treatment B is better because, see, in overall thinking, okay, whatever I put it together, 83%, okay, is higher than 78%. But this time, the pattern in the individual data disappear, right? Is the pattern in the individual part disappear? Definitely. And if you look at the individual data, treatment A is better. But if I look at the compound, now, treatment B is better. Okay, so I make this conclusion. Because 78%, no, 83%, I mean, simply say 78%, yeah, less than 83%. So that I can make a conclusion. And based on the overall data, I just combine them together. See, is treatment A, let me simply say A is, no, B, sorry, this time B is better. So, yeah, Fana said B is better, yeah, it's good. So B, treatment B is better than treatment A. How could that be? Is that possible? It's very strange. Why the same data? See, but look at we use the same data. You just look in different part. You either look at the individual or you look at the overall. You can get a complete reverse. conclusion. So we have a big trouble now. So which one is correct? Do you think? Or which conclusion do you believe? If someone publishes the individual data and then you believe the individual. If someone publishes the overall, then you believe the overall. But if you see both of the conclusion, so how do you tell? Any think now? I think this we call it the paradox. This why paradox? It is impossible for the same data to get two completely reverse conclusion, right? At least one is wrong, or both of them are wrong. Anything? Which one you believe? Have you anyone see some pattern? It is possible because of some reason. And after this, I will give you another fake example, fake data that we made, okay? Human being, we made. So you will see, okay? And what the difference. And finally, I can give you the final reason in mathematics. Because of this, overall average is different from average of average. Okay, so don't think if the two parts are small, put them together, is really small? No, never be. Too small put together could get bigger. Or someone you say that's impossible. See, a small number and a small number is impossible to become a big number, right? It's impossible. The two parts are small. I look at it, the average should be small. No, it is not. It's not that the thinking you usually do or we usually do. We need to look at the distribution of the data. Anyone know what is distribution mean? Means how many real number. Oh yeah, Jacob. So try your best. And Jacob, you can not join back. Try to think about the other way. Okay, thank you. If you miss the last part, if you really miss the remaining part, please be sure to catch up by watching the recording. Don't miss, okay? Especially, I don't want everyone miss the last part. And this in mathematics give you a reason. Anything is possible. Depends how you read the data, but not anything that you read is true. Something is false. Something is true. You need to know a real reason. Let me just give you a reason now. See, and this is example. And the background, gender, bias, the second, kidney stone. Both are real data. My conclusion is that both conclusion, no matter is the individual conclusion or is the overall data conclusion, are false. Both of them are false. You cannot believe in any data. The reason is the number. Okay, so everyone now we look at the real reason. So first, do you think we can compare one student with 100 students? This is called the distribution. If I randomly pick one student, look at the score and look at 100 students or all the students in the school, that's completely different. If I randomly pick one student, we have a randomness. You probably pick a student who worked very hard. Probably you pick a student who worked not hard. So that if you pick a small number and then compare to a large scale data, the results is unbelievable. Don't look at the results. And here is the first. 4,000 is much smaller than 8,000. Okay, so we have some other policy. Okay, probably like the policy we say, our school will get the same amount of female students and the same amount of male students to the school, so that, okay, so the female student and the male students will balance. So that kind of a policy. If I do that kind of policy, what kind of results we will get? Because you have more male students, so that the percentage should be lower than the percentage of the female. Does that make sense? Means if I just look at the percentage, it is not make any sense. Okay, we also need to look at the real data, which is the kind of distribution. And then another distribution here is much even important. Can you look at A, department A, everyone? How many female students apply? Only 100. How many male students apply? She is 8 times of 100. So how do you compare? You have so many male students. Of course, the percentage to get admitted should be lower than. It is normal, right? I don't need so many male students to come to the school. That makes sense? Means the first, if I look at this number means this percentage lost the meaning, lost the meaningness. And then the second, you see, can you compare 25 students to 560? It is not, okay. Meaningless. Meaningless. It makes sense? And then the same, you can look at the other distribution. Okay. The comparison or the method of analysis is unbelievable because the two data are completely not in the same level. Like here, this class is only 2 students. Another class like have 2,000 students. So can you compare the overall? Can you compare what's the points or what's the grades or what's the GPA or the average GPA? That means meaningless because the 2 students has a big randomness. So probably the 2 students are so good, or probably the 2 students are not so good, right? However, if I change a little, if I have a school with 100 or 1,000 students, another school also has around 1,000 students. If I compare 1,000 students to another group of 1,000 students, yeah, that makes sense. Okay, because the more the data I have, and then the randomness will reduce. Okay, because I repeat a lot of times. No, I hope you think about that. Is that true? If you think that true, therefore, so this comparison meaningless. And also you can think about it, these 2 numbers completely not at the same level. One is just a half of the other. And then these 2 percentage also meaningless. Okay. Otherwise, you have to consider the politics or the policy in the school to determine is this comparison is good or not good. So much more work to do. Have we got something? Can you look at the kidney stone case? Now you find something? The first, I said I compare group 1 and group 2. I even did not look at how many patients we enrolled. And then I directly compare the success rate. It is not a good strategy. The strategy is not good. Can you see 87 patients here in group 1, but 270 here in group 2. And this number is much smaller than this number. It's similar like if I have 3 students here and 3,000 students there. You can just look at the comparison is meaningless. So here also has kind of a reason. And look at the second. Here is 80 patient. Here is 263 patient. So because the number of the patient enrolled in each group are completely not in the same level, so therefore we usually, I think you have this kind of knowledge, basic knowledge. Okay, the clinical trial. If you want to do comparison, see, these patients is too many, and this is too few. So how to compare? This is not a good data. The data set is not good. Because probably at the beginning of the clinical trial, when we enroll patients, we did something wrong. We should get this, we should increase more patients in this group. Okay, so that we have a kind of same level. Do not need to be exact number, do not need to be exactly the same, but we hope we can have the same amount of patients in these two groups. Okay, therefore we have a good comparison, but this is not. And then the same, because these two numbers are not at the same level, so the data is not good. Therefore, the comparison should be not reasonable. So therefore, the first conclusion, based on the individual data, no, I don't believe, because this is not a good research. This is not a good research. And then the same, if someone look at it, yeah. So how about the overall data? Oh, you probably say the overall data is good. See, because I have the same number of patients, 350 and 350. Okay, if I look at this number, it is good. But we only look at the number, it's not good enough, right? When we really do comparison, we cannot compare a small kidney stone patient to a large kidney stone patient. Do you think the treatment should be at the same level? No. We have to separate. Small is small. So small use small, use treatment for small kidney stone. And the big kidney stone, we should think about the same kidney, big kidney. I mean, so first step, if we just merge all the data together, this kind of analysis at the beginning is wrong. Okay, it is not reasonable. So therefore, so this is not good. And we should think about it this small. But the small, the data distribution is not good. So therefore, nothing. Okay. At least we say this research is not good, is not so good, because they miss something, miss some real information. Okay. Or the real distribution is not at a good level. Is that okay for you? So far you get something, right? Therefore, I just tell you, if in the future you learn this kind of statistical analysis, okay, the statistical analysis just gave you, if you only look at the conclusion, no, don't be easily convinced by the report. You need to look at the background, look at the raw data, or how the author or the reporter reached to the conclusion. You need to see if the method is logical or not logical. The last example, now I make an example. Okay, so we made so our math department made another example. That's a fake one, but give you a kind of a think, because the distribution different, completely different. Therefore, anything is possible. Anything is possible. Any questions so far, everyone? Have you got it? For the reason, okay, so different one probably introduce different explanation. At least you need to know. And if you look at the report from data analysis, you look at the conclusion, just the conclusion is not good. You have to look at what's the data. Okay, what the data looks like, and then you can make a conclusion. Make sense? And then let's make one. Okay, let's dream that that one. This is a fake one. Okay, fake data. Let's dream that we open a new college, Owens University. Okay, the information about the students and the GPAs for the first year and the second year are given. And our purpose of this question is to compare the first year to the second year. See which year we have a good learning outcome. What is good learning outcome? We use GPA or we use average GPA to tell the learning outcome. The bigger the GPA, and usually we say the better the learning outcome. Makes sense, right? And then, yeah, what does this mean? What does this mean? This means we have a very small, okay, school. This is one male student, so that we have a total 9 male students, okay, and then 1 female student in the first year. This is the first year. The first year. And this is the second year. Okay. So the first year, 9 male students, 1 female, and the 1 female student get GPA 4, means everything is perfect. Okay. And then each male student no get a very bad result is 1 and 1. The GPA is 1. 1 means what? This is A, and the B is 3, C is 2, and then 1 means D, right? So everyone get a D. All you say is everyone get a D, like in this case. So definitely I can calculate for the first year, right? What the average GPA for the first year? Can you calculate average GPA for the first year? For the first year should be equals the total GPA divided by 10 students, right? The total GPA, how many total? 1.0 times 9, because 9 male students, each one only earn 1 point, so total 9 points. And then the female students earn 4. Okay, so that's good. That's due calculation. Divide by 10 should be how many? 9 plus 4 is 13. 13 over 10. So 1.3. Oh, can you see? It's not a good number. Okay. 1.3 means average is 1.3, the GPA for each student. And it's therefore 10 students, the total GPA is 13 points. Okay, so that's the average for the first year. Can we calculate what the average GPA for the second year? Everyone? Let me put here the average GPA for the second year should be this. The second year we change only 1 male student, and then we have 9 female students. Each female student gets 3.9. Is not as good as 4, but it's good. And then the male students gets worse, even worse than 1.0. However, we have something. Can you see? What's the overall GPA? The overall GPA is 0.9, 1 male, and then 3.9 times 9 each, and then divided by 10. I don't know what the number. Should be good number. Can we do calculation? Oops. So 0.9 plus 3.9 times 9 over 10. Is that okay? 3.6. Yeah, so I get a 3.6. 3.6. What does that mean? See, 3.6 is much bigger than 1.3, right? So therefore, the second year is better. Is that okay? So conclusion easily to make. So now we can make a conclusion. Conclusion. So we look at the overall. This is the overall. Okay, so this is the overall. Sorry, overall. Overall data or overall average. Okay, so the total average GPA is 1.3 to 3.6. So that this is the overall. And then we get the second year. Okay, so the second year is much better than the first year. Okay, but this is one. Can you look at the second conclusion? If it's individual, what does individual mean? This time, individuals or look at the male compared to male. Can you compare this? Male compared to male. And then female compared to female. But that's also logical, right? So we just say similar like a kidney stone, we have a small and a large. So compare the patient among small stone. Compare the patient among large stone. Okay, so we look at the detail. What kind of a conclusion you can make? So the first year, each male students get 1. So the average of the male students is 1. GPA is 1. And the second year, the average of course is 0.9. They get worse. Get worse. Make sense, right? So for male students, the second year worse. So the first year is better. And then the same, the first year, the female students 4.0 is bigger than 3.9. So the first year is better for male students, also better for female students. Therefore, the first year should be better. Okay, no matter it's for male students or female students. I can get this. The first year outcome, okay, learning outcome for the first year is better than the learning outcomes for the second year. Oh, it's very strange. Can you see it now? And these are two conclusions completely reverse. Okay. Completely reversed. The pattern disappeared. And this is a Simpson's paradox, right? So always, this is a Simpson's paradox. If I look at the individual, the overall, the pattern disappear or reverse. Okay, so these are we call the Simpson paradox. You say now, because you know the reason, right? And then can you say, oh, why these Simpson's paradox will happen? Because this comparison is completely meaningless. Can you compare? Can you compare 1 male student to 10 male students? No, usually we will not do this. Okay, it lost the meaningless. Okay, of the average. Can we compare 1 female student to 9 female students? Also, it's not a good comparison. So therefore, the individual comparison is meaningless. So how about the overall? The overall, because the male and the female completely different. So probably the female students worked much harder, okay, and they did much better results, okay, than the male students. So therefore, if you put the male and the female students together to evaluate the average GPA, it is not a good. Make sense, right? Okay, so this is the fake data. whatever. I hope it, because of the distribution here is extremely different. One compared to another large number. So therefore, we say the distribution are completely different. The comparison is not good. Okay, the result is unbelievable. We still have one question did not solve. How could this possible? Or we back to here. How could this possible? This number bigger than this number. This 73 bigger than this 69. Why we put the two big number together? I get a smaller number. 78 is less than 83. Similar as another two. Is that possible in mathematics or in our real life? It is. Okay, it is. And the two big number, but this is not the number. Remember, it's average. Okay, or we simply say this is the average. This is another average. Average of average. Do you think we can get the overall average? No. This 78% is not the average of 93 and 73. You can think about it. What is the average of 93 and 73? Should be 83, right? Average should be 83, but it is not 83. Means the overall average is not calculated as the way you think or we think. It's not the average of average. The same. 87% and 69% put together get a big number because this overall average is not the average of these two. Let me put the last one. I hope you are here. Okay, the last. It is possible, okay, because how to calculate the overall average is not the average of average. Like look at the last one, okay, the last one. Can we look at the data? Let me make it small, make it this one. But look at 5, 5, 5, 5, 4, 5, 6, 7, 8. Okay, I look at them. So these are my data. I have this number. How to find the average? How to find the average? Yeah, so I do this. I find the average of this. Okay, so the average of this is 1. I find the average of this. This the average of this is 5. And then I put these two together. I find the average. So that the average or the overall average equals 1 plus 5/2, which is 3. Is that true? Anyone get me? Oh, I have all the data there. Do you think the overall average is 3? You say, oh, this is super easy to get. So that's the wrong thinking, okay? And we usually make, it's very easy to make a mistake like this way. I just tell you, this is the wrong thing. This is the wrong method, okay? Make sense? Wrong. Who tell you to do the calculation? No. The overall average is the sum over the number of the data, right? You need to add the 1 to 1 and then add all these 5 together, add it together to find the sum. And then divide it by how many total data number. Here is 8 data. So you can see. So here is just 2 data points. So here is 2 data points. The first part is 2. The second is 1, 2, 3, 4, 5, 6, 7, 8. You have 8 data points, okay, or data numbers. 2 and 8 are different. So that's similar as the distribution I just showed. If we see these two parts have a different distribution, so the way of average is always wrong. So therefore, what is the overall average? So we can see and calculate the overall average. So think about it. Overall average should be this. The sum over n, which is the number, okay? Or you say it's just the sum over the number of the data points in total. And then we do calculation. 1, I have 2 1s. 5, we have 8 5. The number of which is 10 in total. And then we do is 42 over 10, which is 4.2. Can you see? If you want to find the average, this is true. That's the correct way to find the overall. And that's the wrong way to find the overall. This is wrong. 3 completely different from 4.2 and the last. And then you can see something. This average linked to these 2 and 8. Okay, can I just visualize the last? And you will see where is the overall average. Okay, so I do a little bit. If this is the data point, okay. Let's see. 1, I put a 1. How many ones? This is a 1. This is a 5. I have a 1 and 2 ones. That makes sense, right? How many 5? 8 5, so I have 1, 2, 3, 4, 5, 6, 7, 8. You can imagine. So, and the 3 is in the middle. 3. So what is this 3? What is 3? We just see 3 is the average of averages. Okay, 3 is the average of 1 and 5, but this is not the overall average. I calculated the overall average is 4.2. Where is 4.2? 4.2 is here. It's very close to 5. And this, okay, is the overall average. Is that true? Why this is very close? Okay, so this point that you see is close. Okay, this overall average is close to 5, and here is far away. If I put it like this, and this is close. Okay, closer, and this is far, and this is normal. Okay, why? Because why the overall is close to 5? Because we have more 5 here. Because more weight on 5. So therefore, you can come out of this kind of a conclusion. And if we have 2 type of data, and which data has more weight, the overall average will be close to that number. Okay, so therefore here, okay, it's much closer to 5 because we have more 5. And here for 1.9, so look at here, the final average is 4.6. Why have 4.6? Because we have a lot of data of 3.9. So finally, the overall average will close to 3.9. That's all for today. And that's all for this topic. Okay, so I hope you take some time to work on. You just identify what the Simpson's paradox and know how to do percentage, how to find the overall average. We stop here today. Thank you, everyone. Have a good day.